My name is Manish Gupta, and in this video, I'm going to talk about DALL-E 2 hierarchical text conditional image generation with clip latents. Right. So DALL-E 2 is this popular model that everyone talks about these days. Of course, what is DALL-E 2 useful for? Well, it's useful for text conditional image generation. Right. So previously, there have been several models which could be used to generate images, but without any text conditioning. But DALL-E 2 is one of these models which has been shown to be much better compared to previous model in terms of taking captions and then coming up with images that suit those captions. Vibrant portrait painting of Salvador Dali with a robotic half face, or a living area with a television and a table, or a small kitchen with a low ceiling, or a teddy bear on a skateboard in Times Square, and so on. So Dairy 2 has been shown to generate images which are seemingly realistic but never existed. For example, a corgi's head depicted as an explosion of a nebula. It's very close to paintings. Of course, humans would take a lot of time drawing such kind of paintings, but it very nicely captures whatever is there, the semantics in the title, in the caption, so as to come up with a realistic image. DALL-E 2 can create original realistic images and art from a text description. It can combine concepts, attributes, and styles. For example, these are images about an astronaut riding a horse in in different styles, in photorealistic style, in the style of Andy Warhol, or in the style drawn as a pencil drawing. DALL-E 2 can also be useful for generating image variations. For example, given these original images, you can generate all of these 5 variations. Similarly, given this original image, one can generate these variations. Or given the central image, generating those variations that you see, or given these images, generating variations of this kind. In all of these variations, as you can observe, DALL-E 2 preserve semantic information like presence of a clock in the painting and the overlapping strokes in the logo. It also preserves stylistic elements like the surrealism in the painting and the color gradients in the logo, while varying the non-essential details. DALL-E 2 is also useful for language-guided image manipulations, also called as text diffs. For example, you could come up, you could basically ask for things of this kind: a photo of a Victorian house getting transformed into a photo of a modern house. And as you see, you can actually start with a Victorian house and end with a modern house, and then generate things in between. Similarly, you can start with a photo of an adult lion and then finally end up with the photo of a lion cub and see various stages in between. DALL-E 2 can also help generate image interpolations. So you can actually provide two different images and intermediate variations that you can see. They naturally blend the content and style from both the input images. The same can be seen using another example below. Right? In fact, here are more animations showing how image interpolation, how these text diffs can be used to generate images in between in that senses. Here is a Victorian house being transformed into a modern one. Here is a old. Here is an iPhone being unmodernized to an old phone. Here is a Tesla car being transformed into an old car. And here are Pablo Picasso's The Bull, which is a series of 11 lithographs created in 1945. And this is a nice variation. This is a nice realistic depiction or a depiction of the transformation starting from a realistic depiction, fairly realistic depiction of a bull and ending with just a few lines. In fact, this reminds people of Pablo Picasso's original quote. It would be very interesting to preserve photographically not just the stages, but the metamorphosis of a picture. Possibly one might then discover the path followed by the brain in materializing a dream. So you see how this metamorphosis is actually happening across different stages of the bull. DALL-E 2 can also expand images beyond what's in the original canvas, creating expensive new compositions. So as you see, here is an original image, and there are other frames which are being created by DALL-E 2 until a final big painting gets created with all the surroundings. Notice how nicely DALL-E 2 comes up with various details, and also those details are pretty accurate in the context of the original frame. It can also help make realistic edits to existing images from a natural language caption. It can add and remove elements while taking shadows, reflections, and textures into account. In fact, as you see in this original image, the user can actually specify where do they want to inject a new object. And depending on the position selected by the user, it can seemingly very nicely inject those elements while taking shadows, reflections, and textures into account, giving a very smooth feel. So then what is DALL-E 2's architecture? So all these things are great, but how does it really work? So this picture at the top shows you the broad architecture for DALL-E 2. The figure above the dotted line actually shows training of the clip model, which is used by DALL-E 2. And the figure below is actually depicting the DALL-E 2 model, which is essentially the model which is used at test time. So the clip model is basically a multimodal model which jointly represents an image caption pair. So if you take an image X and a caption Y, a clip model in some ways sort of generates image and text embeddings. You can think of embeddings as mental imagery and mental representations. So clip model sort of takes image X, caption Y, and generates mental representation vectors ZI for image and ZT for text. So that's that. And then the clip objective is to essentially make sure that the image and the text embeddings for the right pair are much closer to each other compared to image embedding associated with some random text pair. ZI, the image embedding, captures all salient features of images that makes images meaningful to humans. So images contain so many things, but what is it that humans focus on? That part is actually captured by the clip model. DALL-E 2 actually uses the clip model and therefore performs text-to-image generation. It in fact combines the clip model, clip embeddings with two important models called as the prior and the decoder. The prior model essentially takes the original text caption Y or the clip text embeddings of the caption and generates a clip image embedding ZI. Decoder diffusion model further acts upon this clip image embedding ZI and generates the original and generates images. In fact, the decoder is more like a clip encoder, inversion of the clip encoder. While training prior and decoder for the DALL-E 2 model, you freeze the clip model. Now, in some ways, the DALL-E 2 model essentially tries to decode what the clip model has captured. Thus, it is a very nice way of interpreting coming up with interpretations of the clip encoding space. Using this notion, in fact, DALL-E 2 can be used to generate image variations. Given an image encoded by the clip model, DALL-E 2 can actually decode with the diffusion model to generate variations of the image. Given two images and their embeddings in the clip space, the DALL-E 2 model's diffusion, you can perform interpolation in the clip embedding space, and then the decoder diffusion model of DALL-E 2 can actually decode an interpolated image. Now, we will therefore now look at how are these prior and decoder models trained in DALL-E 2. There are two ways of training the prior model. Remember, the prior model takes the text caption Y or the text embedding and comes up with the image embedding. Now, this can be done in two ways, autoregressive prior or diffusion prior. In the autoregressive prior, the clip image embedding ZI is converted into a sequence of discrete codes and predicted autoregressively conditioned on the caption Y using a transform model. Again, transform model makes sense here because the input is text caption. On the other hand, one could also use this diffusion prior models. The diffusion prior model essentially takes the continuous vector Zi and directly models it using a Gaussian diffusion model conditioned on the caption Y. It turns out that the authors observed that the diffusion prior model gives you better results compared to the autoregressive AR prior model. This image essentially shows how the diffusion models work. In this particular case, the diffusion model starts off with a random white noise and then slowly over time produces sharper images by doing Gaussian transitions. Now, how is the diffusion model trained? Diffusion prior model trained? Well, the diffusion prior model is essentially a decoder-only transformer because, well, the input is text. It is trained with a causal attention mask on a sequence consisting of these inputs: the encoded text, clip text embedding for the diffusion time step, noised clip image embedding, and also the final embedding whose output from the transformer is used to predict the unnoised clip image embedding. So in fact, rather than actually trying to reduce the error between the predicted noise, in this particular case, the authors attempted to train prior directly to predict the unnoised ZI, the image, rather than just the error part, rather than just the noise part, right? So therefore, you see that a mean squared objective is being a mean squared error objective is being used. However, the objective is being calculated directly on the noised and the unnoised version of the images. Now, these guys also train it with classifier-free guidance, taking learnings from the GLIDE model. So to train it appropriately for classifier-free guidance, this is enabled by sampling. This kind of feature is enabled by randomly dropping text conditioning information 10% of the time while training the diffusion prior model. So in the classifier-free guidance, well, there are cases where you essentially train the model with no text. There are 10% of those cases, and the remaining cases you train with text, such that you can combine the outputs coming from the two versions, the model trained with text and without text, and therefore come up with a more robust model called as classifier-free guidance. More details about classifier-free guidance in my other video where I talked about GLIDE. Now, how is so the second part of this model is the decoder model of the DALL-E architecture, DALL-E 2 architecture, right? So how is decoder model trained? The decoder model essentially follows the GLIDE architecture. It essentially has ADM nets. So it essentially has ADM nets, and how does it basically make use of clip embeddings? Well, it projects and adds clip embeddings to the existing timestamp embedding. It also projects the clip embeddings into 4 extra tokens of context that are concatenated to the sequence of outputs from the GLIDE text encoder. So these things are used across different attention steps in the unit which is the primary architecture used for the decoder. Classifier-free guidance is again enabled while training the diffusion decoder as well, by randomly setting the clip embeddings to 0 10% of the time and randomly dropping the caption 50% of the time while training. Besides the diffusion decoder model, they also have 2 diffusion upsampler models. One is to upsample the output from the primary diffusion decoder model from 64 cross 64 to 256 cross 256, and the other one is actually used to upsample it further to 1024 cross 1024 resolution. For robustness, in fact, the input is slightly corrupted for these upsampler models by conditioning images during training using Gaussian blur or BSR degradation. Upsamplers essentially use unconditioned ADM nets with no guidance and no attention at all. So this is how an upsampling operation happens, and finally, what you end up with is a high resolution image. Now let's come back to this case where text diffs can be generated using DALL-E 2 model. Remember, text diffs basically can basically take an interpolation between this particular text piece, a photo of an adult lion and a photo of a lion cub, and essentially show you the way in which a photo of an adult lion was transformed into a photo of a lion cub. Right? At the bottom, you observe a Victorian house getting transformed into a modern one. This is all possible because DALL-E 2 actually uses CLIP, a multimodal model that jointly learns text and image embeddings. Remember, Word2Vec enabled you to do analogy relationships like woman plus king minus man. In the same way, CLIP embeddings essentially allow you to do such kind of vector arithmetic between image vectors as well as text vectors. Using unclip, we can actually translate points in the clip's concept space back into images and visually inspect the change that is taking place as we move the embedding of an image in the direction specified by the before caption, a Victorian house, and the after caption, in this particular case, a modern house. In fact, the way this arithmetic is performed is as simple as follows. You take the house.png, which is essentially an original house, the Victorian house, and you compute a clip embedding in the image space, let's say ZI0. Similarly, you take the text caption, a photo of a Victorian house, and you compute a clip text embedding ZT0. You take a photo of a modern house, the text caption, and you compute the clip text embedding ZT1. Finally, because you want to move from a photo of a Victorian house to a photo of a modern house, you take the difference vector, a normalized difference vector. What we want to do is to basically start with the original image and essentially subtract, add the modern house and subtract the Victorian house. That is basically move towards the diff vector. Now you could basically do a linear interpolation, also called as LERP, or you can do a spherical interpolation, which basically a spherical linear interpolation, which is basically moving around this arc. So therefore, what people do in this paper is to rotate between Zi0 and Zd using the slurp function, which is spherical linear interpolation defined as follows. And then they synthesize an image from Zi1 using unclip, using the unclip decoder diffusion model. This animation that you see here, it sort of shows the trajectory as t is varied. T in this particular formula is varied from 0, which reconstructs the original image, to 0.5, which sort of reconstructs a modern version of the house. People evaluated DALL-E 2 with respect to GLIDE, and they found that, in fact, the evaluation was done around 3 different parameters: photorealism, caption similarity, and diversity. For photorealism, users were presented with pairs of images, and the users were asked to choose which image looks more photorealistic. For caption similarity, users were additionally prompted with a caption and must choose which image better matches the caption. For diversity, users were presented with two 4x4 grids of samples and must choose which is more diverse. Of course, the users also had an option to choose not sure as an option. So from the results, it was observed that diffusion prior performs better than the autoregressive prior in pairwise comparisons against GLIDE. Now, as you observe here, humans actually slightly prefer GLIDE. So these values that you see here is about preference of DALL-E 2 with respect to GLIDE. So in how many cases people prefer DALL-E 2 rather than GLIDE? As you observe, humans slightly prefer GLIDE to unclip or the DALL-E 2 model in terms of photorealism and caption similarity. These values are less than 50%, but closer to 50%, right? However, unclip is strongly preferred over glide in terms of diversity. As you notice, diversity is much better. These values are way above 50%. For unclip, we only guide the decoder, remember. So it was observed that doing classifier guided diffusion did not work really well for the prior, but it worked reasonably nicely for the decoder. So as you notice from this image as well, as the classifier, as the glide guidance scale is increased, you see that at these higher guidance scales, the images generated by DALL-E 2 are much more are comparably photorealistic and caption and have good caption similarity as compared to glide, but then they lead to much higher diversity compared to the glide. People also compared DALL-E 2 with other models in a zero-shot setting on MS COCO dataset. Now, remember these models at the top are not zero-shot, while the models at the bottom are zero-shot. Compared to DALL-E, the first DALL-E 1 version or the GLIDE version, DALL-E 2 actually leads to much lower FID scores, lower the better. So therefore, they are in fact the state-of-the-art FID scores. In a separate study, DALL-E 2 was preferred over DALL-E 1 71.7% of the times for caption matching and 88.8% times for photorealism. Here is an example showing a painting of a fox sitting in a field at sunrise in the style of Claude Monet, and you can yourself visualize how nicely DALL-E 2 creates much better pictures compared to DALL-E 1, much crisper ones as well. This plot also shows how, with increasing guidance scale, the MS GOCO FID scores increase quite a lot for GLIDE compared to the unclip model, therefore showing that unclip models are better. Remember, higher FID is worse, lower FID is good. Now, it's not all good for image generation models. DALL-E 2 also suffers from some of the standard image generation problems. For example, DALL-E 2 can actually lead to images with biases and stereotypes. A flight attendant as a caption leads to female flight attendants typically. A builder as a caption leads to male builders typically. Although DALL-E 2 has been controlled significantly so as to not generate explicit or offensive content, but it can generate image synonyms which are explicit in nature. For example, for a photo of a horse sleeping in a pool of red liquid, in some ways it can generate this kind of photos which are quite explicit and offensive in nature. It can also generate things which may look like disinformation. For example, smoke inpainted in an image of the White House leads to this image, which can lead to a whole bunch of rumors. It can also generate inhuman, incoherent images. For example, so basically, it can generate images that feel like they are created by an extremely expert painter that has never seen the real world. If you look at the placement of the windows and doors here, in some sense, they do make no architectural sense at all, although it looks cute. Similarly, if you look at this image, it shows the hand so nicely. However, if you notice, the plant is going out of nowhere. The two hands seem to have been conjoined or merged somewhere here, right? Showing completely unnatural image. DALL-E 2 can also lead to incorrect spelling. So a sign that says deep learning, and you see these spellings are completely incorrect. DALL-E 2 lacks basic compositional reasoning abilities. For example, given a caption prompt, a red cube on top of a blue cube, it's not necessary that always you see a red cube on top of the blue cube. In fact, DALL-E 2 or Unclip is worse at binding attributes to objects than a corresponding glide model. If you look at these kinds of problems, they are called as Bongard problems, where the user is given two sets of images, set A and set B, and the user has to formulate convincingly the common factor that A diagrams have, but the B diagrams don't have. For example, in this Bongard problem, the idea is that set A images are all convex shapes, while set B images are all concave shapes. However, DALL-E 2 is not really good at understanding and making sense out of these kinds of problems. Lastly, there are social and technical limitations in terms of Winogrand test. So this is a test which is used to measure vision language models' compositional reasoning behavior. DALL-E 2's behavior is unreliable. Here are 4 examples. Look at the first example. There is a mug in some grass versus there is some grass in a mug. It generates pretty nice images, right? Matching the meaning. There are a bird eats a snake versus a snake eats a bird, or people fall on the leaves or the leaves fall on people, and so on. Right? It generates reasonable images, but if you look at this one, there are fewer forks than spoons versus there are fewer spoons than forks. It actually does poorly here. In general, DALL-E 2 produces nice images. However, its behavior is unreliable. It may, this unreliable behavior is not really very harmful here, but can cause issues in higher stake scenarios. In summary, in this video, I talked about DALL-E 2. DALL-E 2 is a 3.5 billion text-to-image generation model, which combines clip, prior, and diffusion decoder. It generates diverse set of images. It generates 4x better resolution images compared to DALL-E 1, and is preferred by human judges greater than 70% of the time, both in caption matching and photorealism. DALL-E 2 works better with longer and more detailed input sentences. However, DALL-E 2 has its own problems as well. It can lead to incoherent images. It can surely lead to some offensive images, and so on. You may want to try out your favorite caption on DALL-E 2's API here at labs.openai.com. Hope you liked the video. Thank you for watching. Connect with me on LinkedIn here, and look at my research on my homepage here. Thank you.